All right, welcome back. Let's look at another optimization exercise. Here we want to determine a point on the graph of y equals x squared that's closest to the point 18 comma 0. All right, so just imagine you have this situation. The parabola x squared, well, x squared is a parabola, sorry, something like this. That's my ugly rendition of a parabola. Then you have 18 comma 0 is over here somewhere. And so the question is, what is the point that's closest? Oh, is it that point? Is it that point? I mean, I don't know. I mean, it's really hard to guess, without doing the calculus here. So let's take a stab and see what we can come up with. Okay, define the point on the graph of y equals x squared. So some point over here that's the closest to 18 comma 0. What's it going to be? Okay. How might we do this? Well, here we're trying to do what? The point that's closest, we're trying to minimize distance. So what's our distance formula? Good old friend back from what? College algebra, intermediate algebra. Distance basically the formula stems from the Pythagorean theorem. And we get what? X2 minus x1 squared plus y2 minus y1 squared. And then take the square root of it. It's just directly from the Pythagorean theorem. Okay? All right. Now, obviously we have one of these points, x1 and y1. There's your first point. But here's the observation I think that's important. What is the way to describe a general point on the graph of a parabola? And this might seem hard because it's so easy. How do you get to be a point on a parabola? Like, what are the general coordinates of just some generic point on the parabola? Well, they're what? X comma x squared, right? That's just some generic point on the parabola, x comma x squared. You plug in some value, you square it, and that's how you wind up on this parabola. So we can call that our other point because we want to figure out, which one is closest. So let's call this x2. Oop, I'm a little too close to the ribbon up there. And y2. Okay, and now simply plug in to our distance formula. So d for distance equals square root. Now if we plug in, okay, that's x2 and y2 up there. So x2 was x minus x1 is 18 squared, plus y2 was x squared. That was the y value of our generic point, minus 0, the y value of our set point squared. And there we are. Would it be smart to like collect like terms and such for that inside function? It's not mandatory. I guess we could. Here, I mean, I don't think it really matters one way or another. We could leave it as is. I mean, I suppose you could say x squared minus 0 squared is x to the 4th. It's probably good to do that. I'm going to leave this as x squared minus 18 plus x squared squared is x to the 4th. Okay, so there's our distance function. This will give you, if you plug in any x value, this will give you the distance between that point on the parabola and 18 comma 0. For instance, if you want to know the distance between the point, okay, what's a point on here? 1 comma 1. Okay, the distance between 1 comma 1 and 18, plug a 1 in. And what do you get? You get 1 minus 18, that's negative 17 squared, plus 1 to the 4th power is 1, then take the square root. And so the distance between 1 comma 1 and 18 comma 0, that distance is like 17 approximately. If you want the distance between, say, what, 2 comma 4 is a point on the parabola, and 18 comma 0, then plug in a 2 into your distance function. And so that would give us what? 2 minus 18 is negative 16. Squared is 256. Plus 2 to the 4th power is 16. Then take the square root. It's approximately 16.49. So this is the distance here is approximately 16.49. So that distance is less. Okay, and you can imagine doing that for just lots of points and just getting a somewhat reasonable idea of your solution, because eventually they're going to start, obviously it looks like moving 2, we move further to the right, which got us closer to 18, but at some point we're going to move further away. But there's no need to just look at discrete points like that. We can use calculus. Let's take the derivative and find the optimal value. We can minimize the function by finding an extrema, probably a local extrema here. Now notice there is no feasible domain besides all real numbers, right? This point, we could move this point over anywhere. I mean, there is no least x value nor greatest x value, so there is no like closed interval like we had in previous examples. So we're going to be using our techniques of finding local extrema rather than the global extrema, because we don't have a closed interval. We're just looking at x can be any real number we want it to. Okay? So let's find d prime, the derivative. So d prime equals, okay, notice this is a composite function. Composite function. So what is the, here, let's jot this down. The outside function is square root x. Inside function is what? X minus 18 squared plus x to the 4th. So the chain rule says we take the derivative of the outside function, 1/2. We then plug in, it's 1/2 times x times something, it's the negative 1/2 power. But I put that big empty set of parentheses because I know the next step of my chain rule is to plug in the inside function, which is x minus 18 squared plus x to the 4th. Then the last step of the chain rule, the third step, says you multiply by the derivative of the inside function, which is x minus 18 squared plus x to the 4th. Okay, so d prime is 1/2. And we have x minus 18 squared plus x to the 4th raised to the negative 1/2 power times, okay, open your parentheses because there's a couple terms here. Now also notice that x minus 18 squared is composite. So if you want to find the derivative, we have to use the chain rule again. Okay, so what's the outside function here? It's x squared. What's the inside function? X minus 18. So this is actually a pretty easy chain rule. We get what? Derivative of the outside function is 2x. But we immediately replace that x with the entire inside function, which is x minus 18, times the derivative of the inside function, but the derivative of x minus 18 is just 1. Okay? So we get 2 times x minus 18 plus the derivative of x to the 4th is 4x cubed. Okay? Now, what's next? Okay, simplify this derivative. Equals, okay, we have some stuff that's going to the bottom because we have that negative exponent. So we have a 2 on the bottom already, and then we have this x minus 18 squared plus x to the 4th, all raised now to the positive 1/2 because it's on the denominator. Then on the numerator, we have what? Let's do a little distributing here. We have 2x minus 36 if we distribute, plus 4x cubed. And there's d prime. So there's our derivative. There is our derivative. Okay, now we want to set the derivative equal to 0 and solve. D prime equals 0. Now, you're going to hear me say this again. We are working with a quotient. And what do we always do when we're trying to solve quotients set equal to 0? All we have to do is consider the numerator set equal to 0. So 2x minus 36 plus 4x cubed equals 0. Okay. What would I do first here? Ooh, this is a cubic. Interesting. Well, I divide everything by 2, that's for sure. That would give x minus 18 plus 2x cubed equals 0. Yikes. Now this goes back to college algebra. We have to, find maybe rational roots. I'd imagine, that the solution here is a nice rational number. Hopefully, maybe not. Basically, if we can identify at least one root here, then we can factor the rest of it using the quadratic formula, the worst case scenario, or maybe we can factor it by hand. But basically, when you're trying to solve this, you have to factor it somehow, and there's really no super fast way to do this. I don't see an obvious solution here. Like zeros, for instance, is not an obvious solution. We can't factor an x out. So let's see here. How can you find possible rational roots? Okay, this is going to take a little work, guys, this is going to be a good algebraic review. Possible rational roots, so possible rational solutions. And these are possible rational solutions. Are going to be factors of the constant. So factors of negative 18 over factors of the leading coefficient 2. All right, so there's probably going to be a lot of these. So what do you have? Of course, you have factors of 18 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. And then you have all of those divided by 2, so that gives you plus or minus 1/2, 1 over 2. 2 over 2 is 1, we already have that. Plus or minus 3/2, plus or minus 6 over 2 is 3, we already got that. Plus or minus 9/2, and then 18 over 2, that's 9, we already have that. So that's our possible rational roots. And then if you remember the technique from college algebra, you use synthetic division to quickly check which one of those works. Or I suppose you just plug in and see that too. Let's see here. Is 1 a 0? Obviously, 1 is not a 0. Okay. What does it mean to be a 0? It means you make that equation true. Okay. If you plug in a 2, so obviously positive 1 and negative 1 clearly do not work. Here, we're focusing on this right here. Does a 2 or negative 2 work? I don't know. Let's review synthetic division, since that's always a good it's always good to review algebra. So remember, we have to put this in descending order though. So that would be a 2. We're missing a quadratic term, is a 0. A 1 for x minus 18. So you drop the 2. 2 times 2 is 4. 4 plus 0 is 4. 4 times 2 is 8. 8 plus 1 is 9. Oh, hey, I was not expecting that. 9 times 2 is 18. 18 minus 18 is 0. That wasn't so bad. 2 worked. So what? And you can verify that right by just plugging a 2 into the equation to see if it makes a true statement. Let's verify. 2 minus 18 plus 2 times 2 cubed. 2 cubed is 8 equals 0. So 2 is a 0. That means we can factor this as x minus 2, and then this is the remaining factors. 2x squared plus 4x plus 9. Now, Now that we've done that, the rest of this can be factored using either techniques by hand or perhaps by worst case scenario the quadratic formula. Now, does it factor nicely by hand? I don't know off the top of my head. It doesn't have a leading coefficient of 1, so it's kind of hard to tell. But let's see. If it does factor, it'll be x minus 2 times what? 2x and then x equals 0. And maybe if we plug in, I don't know, a 3, we have 3 times 3 maybe. I guess that's the only possibility. Well, a 1 and a 9 or 3 and a 3. Look, I can tell that's not going to work because there's no way, because the 4 is positive, and so we have to have 2 positive factors, but there's no way that's going to work. So I bet we have to use the quadratic formula. So let's back off here for a sec, leave those blank, and maybe let's use the quadratic formula, or we can complete the square. Wonder what you guys would prefer: complete the square, quadratic formula. Let's just do quadratic formula. So x equals negative b. So that's negative 4 plus or minus square root of b squared. So that's 16 minus 4 times a is 2 times c is 9. Oh, I see what's going on here. Over 2 times a, 2 times 2. What do you notice over here? X equals negative 4 plus or minus, we have 16 minus 4 times 2 times 9. 4 times 2 is 8 times 9 is 72. So 16 minus 72, 16 minus 72 is negative 56. So we get plus or minus root negative 56 over 4. What does that tell you? No real solutions. They're going to be imaginary solutions, complex solutions. So here, I'll just do this. Complex. They're going to be, or actually, I shouldn't say, well, let's be more specific. Non-real and non-real. So it'd be x minus non-real, x minus non-real. Okay? So that's going to be, if I use the zero factor theorem, I'm going to get 2 non-real solutions. The other solution will be x equals 2. Okay? So I guess my point that is closest, was I was just kind of guessing over here originally, is the point 2, 4. I would not have guessed that. Okay? Now that's my critical value. I'm going to say solution 2, 4. I only have one real critical value. Now let's make sure it is a local minimum. Okay? Let's just do like a mini first derivative test, because I don't want to do the second derivative. So let's cause obviously look at the second derivative. It's a quotient. It's going to be nasty. Quotient. It's a composite. Require the chain rule. No fun. So let's do a first derivative test. So we look at our intervals, and then we're going to look at the interval to the left of 2. So this would be negative infinity to 2, and then to the right of 2 to infinity. Again, I only have one real critical value, so I only have 2 intervals. My feasible domain was all real numbers. So interval test points. Oh, let's do like 0 and 3. And then we're going to look at the sign of d prime, our derivative. Now let's look at this. The denominator is 2 times the square root. A square root is always going to give you a non-negative output. So in other words, the denominator is always positive. So all we have to worry about is the numerator, positive or negative. So focus on the numerator of our derivative. If we plug a 0 in, is the numerator of the derivative positive or negative? Well, 0 turns the 2 variable terms to 0, and you're left with a negative 36. That bodes well for us. A negative outcome. If you plug in 3, well, 2 times 3 is 6, minus 36, plus 4 times 3 cubed, which is 27. is going to give us positive 78. Again, that's good for us. Why? Because we have our results. We are decreasing, then increasing. So that means we have a change from decreasing to increasing at 2, which the first derivative test tells us that yes, we have found a local minimum. So we do indeed have a solution of 2, 4 that minimizes the distance between 18 and 18, 0 and that parabola. So 2, 4 is if you pick all the points on this parabola, there's an infinite number of points on this parabola. Of all the points on this parabola, the point 2, 4 is the closest to the point 18, 0. And there we are. So, example using the distance formula to find the minimum distance between the point of minimum distance between x squared, y equals x squared, and 18, 0. All right, if you want more examples, I have tons more examples on my YouTube channel. I'll put a link maybe somewhere so you can easily find those. But it's if you look at my old lecture playlist, that's probably the best place because I have a video with probably a dozen or so examples of different optimization exercises, different than the ones you just saw today. All right, I'll catch you in the next chapter. See you then.